All right, so today we're discussing heat transfer. Now, with heat transfer, we're talking about heat moving from one point to the other. And we'll first of all talk about the definitions that are important under heat transfer. Because we have the three main forms of heat transfer, or three main methods by which heat is transferred from one point to the other. After that, we'll look at some applications, some analysis of how this happens. So let's straight away get into some definitions. Now, first of all, the first method of heat transfer we talk about, is convection. Convection is basically that form of heat transfer which occurs in fluids where the movement of heat from one point to the other is with the aid of convection currents. Meaning for this heat to be transferred, that fluid actually completely moves from one point to the other, and along with it, it carries the heat to where it is going. Hence, you see that heat moving. The other one is radiation. Unlike this convection we talked about, with radiation, you don't need a medium because it uses electromagnetic waves in its transferring of heat. So even in a vacuum, you see heat moving from a higher concentration to a lower concentration. The third method is conduction. When you talk about conduction, you're referring to the form of heat transfer which occurs in solids. These solids could be from the same body or perhaps from different bodies, but they are in physical contact. So hence the word conduct or conduction. And basically what happens inside this is that the particles will be vibrating. The little pieces of material inside there will be there vibrating, and with the vibrations, you see the heat being carried or being transferred from one point to the other. And then if you look at convection and conduction, what is common between them is that they both need some medium for heat to be transferred. Whereas if you talk about radiation, there's no need for a medium, but heat is transferred using those electromagnetic waves, meaning even in space, you see heat moving. Now, we'll now delve into conduction. There's what is known as Fourier's law of conduction. In Fourier's law of conduction, it focuses on the rate of heat transfer through the same material, which we can consider to be a homogeneous material. Let me just pick a point again. Where is it? Oh yeah, here. Through that homogeneous solid. And remember that here we said conduction is through this solid. So that rate of heat transfer is supposed to be proportional to the area, which we will be calling the phase area, which is at right angles to where the heat is going, or to the direction of that heat. And also proportional also to the change in temperature with respect to the length, or basically we'll be calling it the thickness of the heat path. The thickness through which the heat has to move. Now look at this diagram. This is now talking about three things. Let me just try to, okay, yeah. In this diagram, what you can see is that there is this thickness here, X, and there are two faces, this face and the opposite face. The area we are looking at, this face area is the same as the face area on the other end, so we'll not have a problem. So as heat moves from point 1 going to point 2, one thing we can all agree is that the temperature has to be higher here compared to where it is going. So heat will move from 1 coming to 2, from a high concentration to a lower concentration. And so we have the thickness. We also have the two temperatures, temperature 1 and temperature 2. So the rate at which heat is going to move is going to be proportional to this We talked about the thickness of the heat path, the temperature difference, and as well as the area. Of course, with all of that with respect to this. Now, let's go to proportionality. We'll say the rate of heat transfer represented by Q with a dot on top is proportional to the area directly and the change in temperature or the temperature gradient with respect to the X, meaning the thickness. A small temperature difference as well as a small or elemental thickness. Now, this is traditional. I prefer we write it this way because we are flipping the way things are done. The negative comes in to tell us that this time around, we are moving from 1 to 2. 1 is at a higher concentration than 2, which is different from the traditional way of doing things where we say T2 minus T1. But here the normal will be T1 minus T2, as we shall see. So with this expression, I pick up this one. When I introduce the equal sign in place of this proportionality symbol, I have to also bring in a constant. A constant, I think from your mathematics, we're using letters like K, maybe C, or something else. But for you at your level, we're introducing this letter here, lambda. So in place of that alpha, we have equals and lambda coming in. The negative is still the same negative. And the other factors are still constant, just like that. Now from your integration, before we even get there, let's get rid of this dx. So we multiply both sides of the equal sign by dx. And the result is this. So the rate of heat transfer multiplied by dx is equal to negative lambda A dt. Now, already you can see that with this, it's already telling us that we need to start the integral issues. Let's try to bring the integrals. Yes, there we are. When I bring the integrals, for the left-hand side, it's fine, because it's just the thickness we're talking about. For the right-hand side, the limits are the two temperatures, the temperature 2 as well as temperature 1. So here, because I already have that negative, it's okay. I can write it like this. Now, here, when we're talking about integration, you remember that the rules of integration requires that we deal with the powers, add 1, then what you do on the powers is also supposed to be the denominator. So what I'm going to do is that I'm differentiating, rather I'm integrating with respect to x on this side. But I can't see the variable there. Where is the variable? It's hidden. There is a number 1 here, represented by the same x, the variable raised to power 0. As we know, any number raised to power 0 is 1. The same thing is happening here. There is nothing here, meaning I have a number 1. So when I raise the variable t to power 0, I haven't changed anything. So t raised to power 0, respecting the limits once again, meaning that when I get to the integration, I'm going to say t raised to power 0. So it's 0 plus 1 over 0 plus 1 in my integration. And so as I do that, here I'll have x being born just like that. I'll have x and q. So I'll have qx on this side. But here I'll have lambda a and t. T, when I try to apply the limits, I'm going to have t2, substitute again t1. So I have t2 minus t1. The negative is still there. So the moment I try to bring the negative into effect, I multiply negative by this and that, then this is the result I'll have here. Now, where's the x gone? Because this is qx as the result. It means that I've divided through by x. That's why the x is still here. So lambda a over x is our result. Now, what are they representing? This is the rate of heat transfer, meaning in watts or joules per second. Then I also have lambda, which is the coefficient of thermoconductivity. Some of the books that you'll be using, instead of this, they use letter K. The interpretation is the same. We just need a variable or a constant that will help us to differentiate different materials. So if you're dealing with wood, the value of this will be different. If I'm dealing with asbestos, it will be different. If I'm dealing with coal and so on. Different metals, including air, it has its own value for this same lambda. Then A, that is our surface area in square meters, or we'll be calling it the face area. And then X is the thickness of the heat path, like we had said. How much distance is it going to go through? What is the thickness through which the heat has to be transferred? That is represented by letter X. So that is what each of those represents. Now, this is for a single wall. What if we have a multi-layer wall? Maybe we have several layers of the same. It's the same expression, but we extend it. We'll have the same negative, but T2 minus T1, or you ignore the negative, but then you have T1 minus T2. Then below here, you're going to have, each of them will have its own thickness and its own thermoconductivity coefficient. So it could be that you have a wall, one layer is cement, the other layer perhaps is asbestos, the other layer is aluminium, and you continue piling up the layers like that. So here, x1 divided by lambda 1, each thickness by its corresponding coefficient of thermoconductivity. So I have x2 divided by lambda 2. We continue like that. Meaning that even if there were 10, we should have gone on adding them up just like that up to 10. So here, if you were to sum them up, summation of the number of layers to get rid of this is what you have. Or perhaps you can switch them around. Of course, this is just a repeat of what is up there. Let's look at an example to apply this. So here we've been told we have an inner plane of a brick wall at a temperature of 40 degrees Celsius, outer temperature 20, thickness 250 millimeters, coefficient of thermoconductivity 0.52, and then we need to find the rate of heat transfer per unit area and the rate of heat transfer through these dimensions of your wall. What information do we have? First, we have the temperatures. Temperature number 1 is 40 degrees Celsius. If you want to convert it to Kelvin, this becomes 313 because you have to add 273. I will talk about that soon. Temperature number 2 is 20 degrees Celsius. In Kelvin, if you were to convert it, it's 293. Lambda, 0.15 watts per meter Kelvin. Now here, let me emphasize, T1 minus T2, 40 minus 20 is 20. 313 minus 293, you still get the same 20. So this conversion to Kelvin is basically not necessary when you're looking for the change in temperature. Unless you're talking about individual temperatures, then it becomes a different case altogether. So when we are using these equations, where it's talking about T1 minus T2, don't stress yourself converting what I did here. It's not necessary. So I did it so that when you are going through, because most of your colleagues were asking about why don't we convert this to the standard unit? The temperature difference, whether in Kelvin or in Celsius, still remains the same. I think basically that's why I did this, for the sake of illustrating. The question is saying per unit surface area, per unit area of the surface. So meaning that our area is 1 square meter. That's the reason we've done that. Let's go then to the solution. This is a single layer wall, meaning that we're going to have that Q equals lambda A over X. Then we have T1 minus T2. T1 minus T2. So since we already have the data, we can substitute. The lambda is 0.15, area is 1, X is 0.25, T1 was 40, and T2 was 20. Here is where I was saying, even if you had put the numbers in Kelvin, what will come from this subtraction will still be the same. So don't stress with your conversion. Just use them. If they're in Celsius, use them in Celsius and continue with the working. When you enter this in your calculator, the answer you should be able to find is 12 watts per square meter. 12 watts per square meter. This is part A. B was asking for the heat transferred. Suppose the area was 2 by 3. So we just multiply that 12 times 2 times 3. Because this last part is representing the area. The dimensions are like length by width according to the way they were presented. So then the 2 times 3 comes in. So when you multiply 12 times 6, here's your answer, 12 watts. Or 12 joules per second. We are losing 72 joules per second, or 72 watts. This is for a single layer, a wall having a single layer, homogeneous material. What if we have more than one layer, different materials? How can you handle that? Look at example number 2. Says a brick wall thickness 250 millimeters, concrete thickness 50 millimeters, then coefficients for brick 0.69, concrete 0.93. The temperatures are 30 inside and 50 on the other side. Dimensions of the wall 10 by 5. So let's then calculate the rate of heat transfer. The rate to amount if heat transferred through the wall per minute. Here we're simply talking about the heat lost per minute. Forgive that English there. Then also the heat lost per hour. Then the interface temperature. Let's pick up the information provided. Here we have two thicknesses. Thickness number one is 0.25 meters because it's 250 millimeters. X2 is 50 millimeters, which is 50 divided by 1000, which is 0.05 meters. Lambda 1 is 0.69 watts per meter Kelvin. Lambda 2 is 0.93 watts per meter Kelvin. The area is 10 in length, 5 in height. So to get your area, you just multiply the two. 10 times 5, there is your 50. We have all the information we need. So there's the 10 by 50, we have the area and all of them. So let's pick up the first part. Of course, the temperatures are T1, 50 degrees Celsius, T2, 5 degrees Celsius. This time, I decided not to convert to the Kelvin because I already explained why there's no need for that. So we'll use them as they are. Let's go to the solution. This is the formula for the rate of heat transfer when you're dealing with a multi-layer wall. The general expression, A, T1 minus T2, then we assemble them like that, each one according to their properties. Thickness, lambda. Thickness divided by lambda, just like that. Thickness divided by coefficient of thermal conductivity for each of them. So with this, we can now just do the substitution. In place of area, I have 50. T1 is 30. T2 is 5. X1 is 0.25. Lambda 1 is 0.69. X2 is 0.05. Lambda 2 is 0.93. So when you enter that in your calculator, what you should find is 3004.213 watts or joules per second. B, we're looking for the heat lost in 1 minute. The heat lost per minute. So heat lost per minute now comes out like this. Here, I'll multiply it by 60 because this is per second. Every minute has 60 seconds. So I'll just multiply that by the 60. So the answer I got, multiplied by 60, 3004.23 times 60. Then my answer is 180,252.809 joules per minute. There was another one which was asking about heat lost per hour. In 1 hour, we have 60 minutes. Each of the minutes has 60 seconds. So if I multiply 60 by 60, it gives me 3,600. So that rate of heat transfer we found, multiplied by 3,600, meaning the answer we had times 3,600, the answer that I should get now is 10,815,168.54 joules per hour. Joules in each 1 hour. If it's not a standard amount of time, maybe you've been given 3 minutes, maybe you've been given maybe 2 minutes. You don't say per 3 minutes, no, you just leave joules and it ends there. Let me repeat. The other answer we got was per minute, this is per hour. But if we've been given something other than unit hour, maybe it's 1.2 hours, 3 hours, something, we don't say per hour, we just put joule and you leave it there. Even with the other amounts of time, when they've been specified, a particular number has been given, other than unit, you just leave it in joules because it's just representing the amount of heat. We have one more troublesome area to handle. Of course, here, I was just trying to emphasize that you can say heat loss per hour there. You don't even mention the per hour again there. What about the interface temperature? Maybe the first question is, what is this interface temperature? The interface temperature is talking about the temperature between the two layers. The temperature between the two layers, that is the interface temperature. Let me just try to pick a pen to try to illustrate. Where here. So we're talking about, is it going to write? Oh, good. Layer 1. And here I have layer 2. So these are the two layers. And of course, they all have the first part here, moving from here to here. That's my first thickness. And from there to there, that's my second thickness. So I have, this is like my X1. So here is my X1. And the other one is X2. You can forgive my handwriting. Guess this is already there. Now, when you notice something here, we are moving from point 1 to point 2 right here. The interface we're referring to is here, where they are meeting, where the layer where the two walls meet. So if this is my T1 and this is my T2, I'll just decide to call this as T to differentiate it from the other two culprits there. So that's the one the question is asking for as the interface temperature. When I'm dealing with the interface temperature, my work is very easy because I'll consider this to be a single layer. Because according to the way heat behaves, the rate at which heat is being lost is constant. The rate of heat transfer is constant. So Q is equal to, I use that formula, lambda 1 area over x1, then T1 minus T, because T1 is higher than T. Temperature is higher at this point compared to what is here in the middle, in between. So that's why I'll just consider this part of the wall and I'll get my interface temperature. Interestingly, even if you decide to use the other part of the wall, you still get the same answers. But you use 2 here, and in the expression, you're going to have T minus T2. The result will still be the same. That was it, by the way. Let's go back to our working. Here I have Q dot being equal to lambda 1 over x1. I have the area here, and I have T1 minus T. So with this in mind, I will just go ahead and substitute. Having in mind that I'm just looking for this T here. This rate of heat transfer, we found it as 3004.213. Lambda 1 was 0.69. Area was 50. X1, the thickness, was 0.25. T1, the temperature this side, is actually 30, minus that interface temperature, the one we're looking for. So it's not known, so we leave it as the subject of the formula. Whatever you do in between, you can feel free to, here there's the 25, you multiply it here and there. What we simply want is for you to make T the subject of the formula. Feel free to maneuver with the algebra. The answer that you're going to find is this, 8.23. Here is a secret. The answer that you got, the answer that we have here as T1, the value that we have here is actually 30. That's our T1, 30 degrees Celsius. On the other side, we have 5 degrees Celsius. Can you see the answer we have here? It's actually 8.23, representing a number between the two values. If you were to find a miraculous answer, which is away from here, meaning it's supposed to be lower than 5 or bigger than 30, then check your work. There should be a mistake. If there is no mistake, that calculator needs to be changed before we change the user. It means you're getting an error from your working. You should have your answer between the two, because it represents a very neat gradient between where it's coming from and where it's going. The temperature should be higher here and lower there. And the value in between should be, yes, representable like that, between 30 and 5. So here we have it, 8.23 degrees Celsius. This is our interface temperature, the temperature where the two layers are meeting. All right. So now it's a chance you can go through this exercise, try to answer those and see if those values will come out just like that. Next, we're going to talk about Newton's law of cooling, which is a continuation from here.